Everybody, we are going to talk about trigonometric functions and the unit circle today. First, I want to talk about radians. As a reminder, we typically understand what degrees are in the US, where if somebody tells you to do a 360, you know that means that you need to turn around, completely do a full revolution, where a 180 is if you're facing the front, you turn and face the back. We need to speak about radians for trigonometric functions in the unit circle. And so as a reminder, radians are a measurement where we have an angle theta and an arc length associated with that angle. So it's a central angle, and we have a radius of length r. So if you look at this diagram, here's the arc length we're talking about. Here's this angle that we're talking about. Let's say it's, B prime, CA prime. And then we have this radius. Well, the arc length S is actually equal to the angle measurement theta times R, whatever the radius may be. And we can actually solve for theta to say that theta is equal to the arc length divided by R. In a unit circle, when we speak about a unit circle, this is a specific circle where the radius is equal to 1. And so in the case of theta, theta is just equal to the arc length. For reference, a circle has a full revolution of 360 degrees. If I look at this circle here, and I have a starting point, the x-axis, let's say that's 0 degrees. If I go all the way around, that's going to get me to 360 degrees. 360 degrees is equivalent to 2 pi radians. If you cut that in half to do 180, that is just pi. Pi is equal to 180 degrees. If you cut 180 in half, where you get 90 degrees, that's equal to pi over 2. Now, there's a chart below that shows degrees, common degree angle measurements. We've got the first 2 quadrants listed, and then key measurements of 270 degrees and 360 degrees. Half of 90 is 45. That's where you get pi over 4. So we've got some incremental measurements of 30, 60, 90, and 45 measurements that we're going to use for the unit circle. We have trigonometric functions that we use in trig and in calculus that we use with a right triangle, where we have the angle and then the side opposite it, the side next to it, and the side across from the right triangle. So when we're talking about theta, it matters where the angle is. The side opposite is from the angle that you're dealing with. Now, I could draw the angle in the upper corner as well, and then the opposite and adjacent would swap. Adjacent is the angle is made with the hypotenuse and the adjacent side, and the side that is not touching for that angle is the opposite. When we use those definitions, we can then say that the sine, not sin, sine of theta is opposite over the hypotenuse, cosine is adjacent over hypotenuse, and the tangent is opposite over adjacent. And then if you notice, the cosecant, the secant, and the cotangent are all reciprocals of those 3 original functions. Cosecant and sine are reciprocals, secant and cosine are reciprocals, and cotangent and tangent are reciprocals. If we circle back to the unit circle, where we have a radius of 1, let's draw our angle theta here, starting at the x-axis and opening up counterclockwise. Opposite of theta is this length right here, which is just the y distance. Next to the angle theta is the x distance. And you notice that point is the coordinate that represents x, y. And then we have our hypotenuse. So this is opposite of theta. This is adjacent of theta. And then we have hypotenuse. And for a unit circle, you notice the radius is 1. And we can then adjust our trigonometric ratios to include the fact that the radius is 1. So your hypotenuse is 1. So everywhere I see hypotenuse, that's going to be a 1. Which means that our sine, the opposite, is just y. So the sine of theta here in a unit circle is the y coordinate. The cosine of theta in a unit circle is the x coordinate. And then the tangent of the angle theta in a unit circle is the y over x still. And then we use the reciprocal. So we have 1 over y, 1 over x, and x over y for those other three. Now we're going to fill in some values in the unit circle, but in order to do that, we need a few special right triangles. So when we're doing Pythagorean theorem, we had a couple of right triangles that were special that we worked with. So those are the ones that we're going to focus on now. With the first special right triangle, it's an isosceles triangle, and in an isosceles triangle, the angles are the same and the sides are the same. So if we're going to apply the Pythagorean theorem, let's say I have some side length of 1 in this case. Then we could determine the hypotenuse. I'm just saying 1 is arbitrary. 1 and 1, they're both the same because it's isosceles. The hypotenuse is found by using the Pythagorean theorem. 1 squared is 1, so we have 1 plus 1, which is 2, is the hypotenuse squared. So root 2 is the hypotenuse here. In a unit circle, we actually have a hypotenuse of 1. So if I divide through by root 2 on each of these, then the hypotenuse is 1, and my side lengths are 1 over root 2. And take a second to talk about rationalizing the denominator. Some of you might have teachers that want you to rationalize, and some of you might have teachers that it doesn't matter. Rationalizing means there is no radical in the denominator, and the way that you do that is you multiply by the radical in the numerator and the denominator. It's like it's a 1. Root 2 over root 2 is 1. 1 times root 2 is root 2, and then the square root of 2 times the square root of 2 is the square root of 4, and the square root of 4 is 2. So you wind up having root 2 over 2. So in this 45, 45, 90 triangle, the opposite and the adjacent sides are both root 2 over 2. Okay, looking at an equilateral triangle here, an equilateral triangle has all three sides the same. And when you cut down the middle, when you bisect this angle, which has all three angle measurements the same, I can create two right triangles together. So let's see what I did with these angles. I have a 60-degree angle here, and then I bisected to create a 30-degree angle here, and then I have the right triangle. Let's imagine that, again, I'm dealing with a unit circle, and I have a side length of 1. That means when I cut this base piece here in half, that's going to be a side length of a half. I have to figure out what the bisecting leg is. If I take 1 squared and set that equal to b squared plus 1/2 squared, well, then I find that 1 is equal to b squared plus a fourth. Subtracting a fourth from both sides, then 3/4 is equal to b squared. If you square root that, you get root 3 over 2, because the square root of 4 is 2. This missing side here is root 3 over 2. Now notice across from the 30 degrees is 1/2. Across from the 60 degrees is root 3 over 2, and across from the hypotenuse is 1 in that unit circle. These are special values that we're going to use. You'll see them in graphs and in lots of calculations that we do when we're taking limits and derivatives and integrals all throughout calculus. Now we're going to move on to actually filling in a unit circle using these special triangles and the trigonometric ratios that we have. Here's my unit circle. In this unit circle, we know that the radius is 1. We have our x and our y, and each point on this circle has a coordinate of xy. I know that we have 0 degrees here and 0 pi. If I go 90 degrees, that's pi over 2. If I go 180 degrees, that is pi. And then 270 degrees, we have 3 pi over 2. And then 360 degrees, we have 2 pi. Now I can fill in other pieces. If I take half of 90, I get 45 degrees, which I also know is pi over 4. The next angle down is going to be 30 degrees, which is pi over 6. 60 degrees would be above 45, and that is pi over 3. Now, each of these values that go around that are marked are equal distance. So the pi over 3 hops over to the next side and becomes 2 pi over 3 because it is also 30 degrees away. That's 120. I'm going to go ahead and fill in these values. Notice that if you're looking at the x-axis, the angles that are directly above and directly below all have a denominator of 6. There's pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. If you look at the y-axis, all of the angles that are directly next to the y-axis have a denominator of 3. You've got pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And then the angles that are in between the 30 and the 60 is 45 have a denominator of 4. Pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. All of the measurements above the x-axis are less than pi because they're less than 180 degrees. All that are below are between pi and 2 pi because they are between 180 and 360 degrees. We can now use those special values to help us determine the coordinates. First of all, in a unit circle, I know that my radius is 1. So at x with a dot, if x is the only thing and I have no y, that's going to be the coordinate 1, 0. At 90 degrees, I have 0x and I have 1 whole for y. Going 180 degrees, I'm at negative 1, 0. And 270 degrees is 0, negative 1. For this 45, 45, 90 triangle, remember that we had 1 over root 2 if you weren't rationalizing, or root 2 over 2. It's the same thing. They're both equal. I just want you to know that if you're Googling or you're looking at the unit circle and somewhere else, you might see 1 and not understand where it's coming from. It's rationalizing to get that root out of the denominator. But in this case, regardless of which angle I'm picking, either 45, the opposite and the adjacent are the same value. The only difference is where it is located in the unit circle. So if I start at 45 degrees, the x and the y are both positive. So to help you imagine the triangle, let's say I made this into that right triangle and this was 45 degrees, then opposite that would be root 2 over 2. And adjacent would also be root 2 over 2. And I know that I said opposite first. Opposite is actually the y value and adjacent is the x value, but they're the same in this case. And any measurement of 45 along the way is going to be the same thing. It just depends on the sign. All of the coordinates and trig ratios are going to be positive in the first quadrant. In the second quadrant, all the x's are negative and the y's are positive, which changes a few of your ratios. In the third quadrant, both x and y are negative, and in the fourth quadrant, x is positive, y is negative. So when I'm filling in the root 2 over 2, that's the same for all of those over 4s. Every denominator of 4 has the same values. It's just the changing of the sign. So here, the x is negative, the y is positive. Here, the x and y are both negative. And over here, the x is positive and the y is negative. Okay, let's move on to the 30, 60, 90 triangle. As a reminder, when we had our equilateral triangle that we were dealing with, 30 degrees was up here, 60 degrees was down here. Across from the 30 was the 1/2, across from the 60 was root 3 over 2, and it was still with the unit circle. For the 30 degrees, opposite is 1/2, which is the y value, and adjacent is root 3 over 2. They switch when you're dealing with 60 degrees, or pi over 3. That becomes 1/2 and root 3 over 2. All of the pi over 6, all of the 6's in the denominators are going to have that same root 3 over 2 1/2 point, and it's the ones that are directly above and below the x-axis. It's just the sign that changes. So this is going to be negative root 3 over 2, positive 1/2. This is going to be negative root 3 over 2, negative 1/2. And this one's going to be positive root 3 over 2, negative 1/2. Ones closest to the y-axis are going to have that pi over 3 value where it's 1/2 and root 3 over 2, but the signs change. Negative 1/2, positive root 3 over 2. This is going to be negative 1/2, negative root 3 over 2. This one's going to be positive 1/2, negative root 3 over 2. So that's how you complete the unit circle with those special triangles and the measurements. Now let's apply this knowledge and see how we can solve problems using this information. So we're going to find some trigonometric ratios, and we're also going to use a triangle that may be not a unit circle. Here is that unit circle off to the right. What we're going to do is we're going to write the XY pair for each of these values and then use that to help us determine sine, cosine, tangent, cosecant, secant, and cotangent. Remember, in a unit circle, sine is y, cosine is x, tangent is y over x, cosecant is 1 over y, secant is 1 over x, and cotangent is x over y. We didn't talk about negative angles. Well, a negative angle is going to have the same value as a positive angle. It's just a difference of 2 pi. So if we are at negative 3/4 pi, and I need to figure out what that is, what I do is I add 2 pi to that. 2 pi is the same thing as 8 pi over 4. And that gives me 5 pi over 4. So this angle measure of 5 pi over 4 is the same as going back negative 3/4. That has a coordinate of negative root 2 over 2 and negative root 2 over 2. For negative pi over 6, negative pi over 6 plus 12 pi over 6, that's 2 pi, gives me 11 pi over 6, which means we are using this value here of root 3 over 2 and negative 1/2. 0 is going to have an xy of 1, 0. Pi over 3 is going to be 1/2 root 3 over 2. And then 3 pi over 4 is negative root 2 over 2, positive root 2 over 2. So pulling the sines and cosines should be very easy. Sines are all of the y values, cosines are all of the x values. I'm going to do that for each of these. All of the y values. And then all of the x values. Now, when you are doing tangent, you're stacking fractions. And when you divide fractions, you actually multiply by the reciprocal. Tangent's pretty easy, cotangent's pretty easy because they are dealing with the same number when you're dealing with fourths. Negative root 2 over 2 divided by negative root 2 over 2 is 1. This is negative root 2 over 2 divided by negative root 2 over 2, which gives you 1. And the reciprocal of that is 1. Tangent here, y over x is 0 over 1, which is 0. And then the rest we have to deal with fractions. This is negative 1/2 divided by root 3 over 2. So you're actually multiplying by 2 over root 3. Gets a little complicated in here. The 2's cancel, and you have negative 1 over root 3. If you want to rationalize that, remember you multiply by √3 over √3. The reciprocal of that is negative √3. So one benefit of not rationalizing is it's easier to take the reciprocal. For tangent here, I've got √3 over 2 divided by 1/2, multiplying by 2 over 1 just gives me √3. And the reciprocal of that is 1 over √3. So notice that the cotangent and the tangents are opposite on those, from pi over 6 to pi over 3, because they're switching angles. And then √2 over 2 divided by negative √2 over 2 is -1. And the reciprocal of -1 is -1. What about when I take the reciprocal of 0 over 1? 1 divided by 0 is undefined. That does not work. Okay, let's fill in the reciprocals of the others. Taking the reciprocal of sine gives me negative √2. Think about sine before. Remember I was saying it was 1 over √2, and then we multiplied to rationalize that. So the reciprocal is easier. Same thing with the secant here. Reciprocal of -1/2 is -2. Rationalizing, this is the reciprocal of this is 2 over √3. If you rationalize, it is 2 √3 over 3. The cosecant, again, 1 over 0 is undefined. That does not work here. And the reciprocal of 1 is 1. The reciprocal for sine here is 2 over √3. The reciprocal of 1/2 is 2. For the reciprocal of 3 pi over 4, I have √2 and negative √2. Let's do one more problem where we're going to be given a specific trigonometric value, and we need to use that to complete the ratios. We have sine of x equal to 7 over 25 within a certain interval, and that interval is from 0 to pi over 2, which means I'm in the first quadrant. So I have my circle, and remember that this is 0, this is pi over 2, so I'm talking about in this quadrant here. On my circle, which it doesn't say it's a unit circle, it says that the sine of x is 7 over 25. So 7 is the numerator, which is the opposite. 25 is the denominator, which is the hypotenuse. And I need to find this side length. Let's call it A. I use the Pythagorean theorem. A squared plus 7 squared equals 25 squared. A squared is then equal to 625 minus 49. Subtract 49 from both sides, and you get that A squared equals 576, where A is then 24. If I know 24, I then find the cosine, because that is adjacent over hypotenuse. The cosine of x is then equal to 24 over 25, and the tangent of x, which is opposite over adjacent, is 7 over 24. Hope you found that helpful. Thanks for watching.